All right, welcome back. So we're going to talk a little bit more about electrophilic aromatic substitution. We're going to do the last little dregs of that, get through some of the directing effects, and as it comes to synthesis considerations, then we're going to get into, instead of electrophilic aromatic substitution, we're going to get into nucleophilic aromatic substitution. There's only a brief discussion to go through about that. And then we'll do, but that will involve a new reaction mechanism. And then we'll do one more reaction called elimination addition. Again, that's a new reaction mechanism as well, but it's interesting in the sense that it goes through an interesting intermediate. And so without any further preface, I want to go ahead and get this started. All right, you guys remember how to balance reactions? All right, so where do we leave off? When we're talking about the directing effects of different substituents on a benzene ring. And what I want to do is I just want to summarize some of these things. And by summarizing, I'm just going to say electron donating groups, remember, they're activators. That means the next electrophilic aromatic substitution reaction goes faster than the previous one. And I just want to remind everybody that if it's an electron donating group, an activator, then what do we have? The directing effects are ortho and para. And so that means that if I'm going to put some groups on there, they'll either be at the ortho positions or at the para positions. And so I'm not saying that we would add all three groups. I'm just saying that these are the positions where we might undergo electrophilic aromatic substitution. And which of these positions it actually undergoes depends on the identity electron donating group. But here's the general directing effects. The same thing goes with electron withdrawing groups. Oh, thank you. Did not see that. Let me leave these. Let me pull my chat up too. Okay, yeah. So everybody should be in now. Sorry about the delay. So the same thing goes with electron withdrawing groups. They're deactivators. And that means that the next electrophilic aromatic substitution goes slower with respect to benzene. And so if I have an electron withdrawing group, then the directing effects of electron withdrawing groups are to the meta position. And so if I were going to add a group that on this ring, it would be at one of these positions. Of course, in this case, the example molecule is symmetrical, so the spots are equivalent. That's not necessarily true every time. There was only one exception, and the exception involved a halogen attached to the ring. It is a deactivator. So the reactions, subsequent electrophilic aromatic substitution reactions do go slower than one without the halogen on it, but it still nonetheless directs ortho and para. And so if there were going to be an addition after that, it would be here at the ortho and para positions. Okay. All right, so that's if we're dealing with monosubstituted benzenes. So if we just have one group on it, it becomes pretty straightforward trying to decide where the next group will get added. The challenge comes up, and I think we did talk about this a little bit. The challenge comes up when we deal with a disubstituted benzene. What if I have this guy? Well, now what we need to do is we need to figure out the directing effects. In this particular example, when I look at CH3 and NO2, I say that CH3 is an ortho-para director. I don't need to think about para because it's already got a group on it. But when I think about nitro, it's a deactivating group, so it's a meta director. So in this particular example, both groups are directing to the same position. So as long as that's the case, there's no consideration to be made about where the subsequent electrophilic aromatic substitution reaction takes place. The problem arises when the two groups direct in different directions. So let's put a methoxy on there and a CH3 on there. Let's do the nitration again. And let's examine the directing effects. So the CH3, again, ortho-para director. We don't have to think about para because it's busy. The methoxy group is also an activator, right? It's a moderate activator. So it directs ortho and para as well. Again, para is busy. So what's the major product? How do we decide where is it going to be? Because the directing effects aren't in the same position. Well, in the cases where there's more than one directing effect, the stronger activator determines the directing effect. And so that means that the nitro group adds at the blue position because the methoxy group is more strongly activating than the methyl group. And so that's when it really comes down to it. And so it really, you have to decide which one is the stronger activator. And so what I want to do is I just want to give one quick example just to summarize this in a nutshell. Let's take alcohol, let's take CH3, and then let's do this carbonyl group. So what do we get here in this case? Well, the CH3 is weakly activating. The OH group is a strong activator. And this is a moderate deactivator. And so when I think about it, I say, well, which one is the strongest activator? In this case, it's OH. And so OH is going to determine the directing effects. It's an ortho-para director. Two of those, one ortho position and one of the para positions are already taken up. So it looks like this is the spot that is most likely to do electrophilic aromatic substitution. And so usually I'm going to be asking you, and other practice problems will be asking you to sort of sort out the major product, and that's the way that we would do that. All right, there's a couple of more considerations to make besides directing effects. We also need to consider sterics as well. Steric effects definitely play a role in directing. So if I take a bulky group like isopropyl and I do a nitration with it, there are two possibilities. I'm going to move the nitro group. I'm going to move the isopropyl down. I got this one as a possibility, but this one is also a possibility since the isopropyl group directs both ortho and para. It turns out this one is the minor product and this one is the major product simply because of the steric hindrance at these locations due to the bulk of the isopropyl group. So this is true, the same is true when it comes to disubstituted rings. So if I have isopropyl and ethyl, they're both ortho-para directors, so that means there or there based on which group I'm thinking about doing the directing. And so it turns out in this case, it's going to, the more favorable location one will be the one that is positioned at the ortho position to the less bulky group. The next consideration, the one that actually brings up the most problems, is what if the disubstituted benzene, so that one was 1,4, what if it's 1,3? What if it's like this? And so let's do the nitration now. HNO3, H2SO4. What are the three possibilities? So I've got this guy directing ortho and para. So this group directs ortho and para. This group also directs ortho and para. And so which one of these positions is more likely to undergo electrophilic aromatic substitution? What are all of the possibilities? Well, I could have one attach here. I could have one attach here, and I could have one attach there. And so when it comes to the distribution of products, this one is the major product, this one is the minor product, and this one is not observed. There's too much steric hindrance at this position due to the fact that it's sandwiched in between two groups. So there's a little bit too much going on in this spot. This one is the major product because it's ortho to the smaller group. This one is the minor product because it's ortho to the larger group. Any questions about that? Just want to make sure we're on to good to go with that. That's sort of a review of what we talked about in our problem solving session. All right, so here's something that's just that's new. What if though, what if I actually wanted to synthesize the following molecule? What if I wanted to take this isopropyl group and I actually did want to install something in that ortho position like a chlorine? Well, we've already said that I can't just do chlorination because the directing effects, although they are ortho and para, the para position will be favored based on the fact of the limited steric hindrance. So I was asked to repeat what I said about the large group. Was that in the previous? So if you can still kind of see in the corner, that one will not be observed because it's sandwiched between two big groups. So it's, even though ethyl group is kind of small, it's next to an isopropyl group, which is clearly sterically hindered. So this one is not observed at all. This one is the major product because it's ortho to the ethyl group. This one is the minor product because it's ortho to the isopropyl group, and the isopropyl is larger than the ethyl. And so that's what determines that it's minor versus major. Hope that cleared up for you. Hope that cleared it up for you. All right. Cool. So what if I did want this installation of this chlorine at that location? I know from the previous discussion that the para position will be favored due to the sterics. So what I can do is take advantage of another one of our reactions that allows us to do that. If I have the isopropyl group to start with, I could do sulfonation, H2SO4 fuming. And all of the same chemical or regioselective outcomes would be observed. That group would be installed in the para position. And then I can do chlorination. Now, we can take a look at the directing effects. The directing effects of the isopropyl group are ortho and para. Again, para is busy. And it turns out that this is a deactivator. It's going to direct meta. And so at the end of the day, they're both directing to the same positions. So when I do the chlorination, I'm going to get the chlorine attached where I want it to, or where I want it to be. The only thing I have to do now is remove that group to get rid of the sulfur-containing group that I don't want. And so what we're doing is we're taking advantage of the idea that this sulfonation actually exists in an equilibrium where fuming H2SO4 installs the group, but dilute H2SO4 can remove the group. And so this whole thing is called a blocking group. I think I might have mentioned this in passing. We're using this sulfonation to provide a hindrance to the site where we don't want a group to be added, and then taking advantage of the fact that we can easily remove it. All right, so this is how I would use this in as a blocking group. And this will become important in synthesis because I may give you a synthesis problem where I want the group attached at the location that would be unfavored due to steric hindrance. And so that means that you'll have to do something to prevent the chlorine or whatever group I'm looking at from adding to the position where I essentially don't want it. And so that's where this blocking group will come in handy. All right, so let's review the reactions that we have from a synthetic standpoint. All right, we know how to make all manner of monosubstituted benzene rings. So we can start from benzene and we can do some reactions. It might be one step or it might be 2 steps, but we can install all manner of groups. And so what can these groups be? Let's think about it. It can be Br. It could be Cl. It could be NO2. What else have we done? We just talked about sulfonation. We could also add an R group where we do have to make some considerations for the R group. We have to worry about the possibility of rearrangements. But what else could it be? It could be an acyl group. We don't have to worry about rearrangements with acyl groups. We can take an NO2 and we can convert it into an amine group. We can take an R group and convert it into a CBr3, and we can also take an R group and turn it into a carboxylic acid. So these are all of the groups that we've learned about putting on this ring in 1 or 2 steps from a synthetic standpoint. Those are fairly straightforward. And the reason they're fairly straightforward is because we don't have to really think about any of the directing effects of multiple substituents. It's really then when we get to disubstituted and multiple substitutions on these rings that we really have to think about what's going on. And so let's take a look at an example of that. There's the first level of, I'm just going to break it down into levels. I'm going to call this one level 1. This one's fairly straightforward. The only consideration that you have to make in a level 1 example is what are the directing effects? And so what order should I do the reactions in? I've got 2 choices. In the first path, I could do nitration followed by bromination. In the second path, I can switch the 2. I can do bromination followed by nitration. But only one of these will actually yield the product that I'm looking for. Let's take a look at the directing effects to decide which path is correct. We know that bromine is a weak activator. Bromine is a weak deactivator. It's the exception. It is a weak deactivator, yet it directs to the ortho and para position. So if bromine is on the ring first, then it's going to direct in a location where the nitro group is not where I want it. So if I do bromination first, I end up with the possibility of having a major and minor product, major in the para position and minor in the ortho position, but neither one of those are where I want them. If I think about the bromine, if I think about doing the nitration first, then the nitro group is a deactivator, a strong deactivator, and it directs to the meta position. And so that's where I want the bromine. I do want the bromine at the meta position with respect to the nitro group. And since the 2 meta positions are equivalent, I only get 1 product. So I know now which path I must take from a synthetic point of view. Path number 1 gets me to the product that I want, and path number 2 doesn't, even though it's the same set of reactions. And so that's something that I really need to make sure that I'm keeping in mind when I'm doing synthesis problems with benzene rings and using electrophilic aromatic substitution. Well, that's just level 1 though. So that's just the very basic thought when it comes to disubstituted benzene rings. I'm going to have an example for you at what I'm just going to call level 2. This is the next level. And the basic idea behind this extra bit of complication is that directing effects change due to a change in an attached group. Essentially what I mean by that is that an ortho-para director has something done to it that changes it into a meta director or vice versa. That's what I mean by that. And so let's take a look at an example of that. If I have a molecule where I want an amino group and a chlorine group meta to it, one of the things that I want to point out that is that this can't be done. I can't make an amine group, can't do that in one step. We don't know a way to do that in one step just yet. So what does that mean that I have to do? Well, that means that I have to do a nitration first. I have to do nitration followed by a reduction of the nitro group into the amine group. Well, let's take a look at it. This group in and of itself is an ortho-para director, and so is the chlorine group. They're both ortho-para directors, and so it doesn't matter which one of those groups I have on the ring first. Neither of the subsequent electrophilic aromatic substitution reactions will go into the right position. So what do I do then? What do I do at that point? So I can't have Cl on first, and I can't have the amine group on first either, because they don't direct in the position that I want. But I know that the nitro group is electron withdrawing, and therefore it directs to the meta position. So starting with benzene, I now do have an idea of what I need to do. If I do nitration first, then I get the nitro group on the ring. It's now deactivating in an ortho-para, and a meta director, and the chlorine is in the meta position. So if I add the chlorine next, it will do the directing that I want it to. In other words, chlorine will be directed to the meta position. And now I can reduce. Now I can reduce the nitro group to get the amine group that I want. And so the correct order of synthesis steps would be HNO3, H2SO4, then Cl2 and AlCl3, then zinc HCl, and then sodium hydroxide. No other order of synthesis steps would work for synthesizing this particular molecule from benzene. So even if you have all of those steps, but you don't have them in the right order, it's not going to be a situation where you're totally correct. So we started off thinking about blocking groups. So that sort of introduced us into the synthesis discussion. Then we thought about what we can add as far as monosubstituted benzene. Then we thought about level 1 disubstituted benzenes. That was a level 2 consideration. In other words, what happens if the directing effects of a group changes throughout the process of the synthesis? There's just a couple of final rules that I'm just going to throw out at you for directing effects, or excuse me, for synthesis consideration. All right, so you can't do nitration on a ring with an amine group. And the reason is that HNO3 and H2SO4 will oxidize the amine group. And you'd get a messy soup of unseparatable products. The other one I think I've already mentioned before, and that's about doing Friedel-Crafts acylation or alkylation on a ring that's deactivated. So you cannot do Friedel-Crafts alkylation or acylation on a ring that is strongly or moderately deactivated. So that implies that if a nitro group is on the ring, then you can't do another Friedel-Crafts alkylation or acylation. So this does prevent, or it doesn't prevent, but it does lead you into some conceptual bottlenecks so that you know, well, if I've got a nitro group and I need to install an R group, I can't install the nitro group first because it's too deactivated. And remember, a strong deactivator example would be nitro. This would be strong. And a moderate deactivator would be this one. And so you can't do any sort of Friedel-Crafts acylation or alkylation in those cases. All right, let me just pause for a beat, because right there, that's the end of electrophilic aromatic substitution. I did warn you at the beginning of this discussion that there would be a lot of things about electrophilic aromatic substitution. The first things we did was we learned the basic mechanism. And then we went through all of the different possible reactions of benzene going through an EAS mechanism. Then we started to think about the directing effects of these different groups when it comes to the next electrophilic aromatic substitution reaction. And we really did spend a lot of time talking about how those things are shown to be directing one way or another way. So the question is asked, can you use the Clemenson reductions to bypass the moderate ACL group, the moderate acyl group? And I think, if I'm not so great with names, but you'll have to type yes in chat if I'm on the right track, you mean installing an acyl group and then reducing it into an R group, which is one of the ways that we use to deal with the possibilities of rearrangement. And so the question is absolutely, right? So once you've installed that acyl group and you reduce it into an alkyl group, it's no longer moderately deactivating. In fact, now it's activating. even though it's weakly activating. So yes, in that case, you don't have to worry about it. Yeah. All right, and so after we thought about the directing effects, but then I will remind you, we really did dig into the individual mechanisms and resonance structures of some of these groups to figure out if they were electron donating and electron withdrawing. Remember, then there was a discussion about the exception that is the halogens. And then we really dug into this bit about directing effects and synthesis strategies. So there's a lot going on here with electrophilic aromatic substitution. There's two other reaction mechanisms that operate on aromatic rings: nucleophilic aromatic substitution reactions and elimination addition reactions, but they're by far less considerations to make. And so let me give you, let's start off with nucleophilic aromatic substitution. So if I have a bromine and a nitro group, then I can react it with some sodium hydroxide, heat it up a little bit, and then react it with some acid. I can replace, in other words, substitute the bromine group for an OH group. If I do this same reaction where the nitro group is there, I observe the same type of substitution reaction. However, if I try to do this reaction where the nitro group is meta from the bromine, I observe no reaction. Okay. So these reactions would definitely go on the reaction board if we were in the face-to-face course. So that's definitely something that you should have committed to memory. And then what I want to do now then is just kind of list some of the things that we're seeing as we can summarize from these reactions. The ring must have a powerful electron withdrawing group. Typically, we're talking about the nitro group. The ring must have a good leaving group. And then as you saw, the electron withdrawing group and the leaving group must be ortho or para to each other. Otherwise, there's no reaction. Okay, so this is nucleophilic aromatic substitution, and we can show why that electron withdrawing group needs to be in a ortho or para position by taking a look at the mechanism. And so this is the nucleophilic aromatic substitution reaction mechanism. Hold on, what's the third? The question is asked. The third what? The third rule? Oh, the third rule. The third rule is that the electron withdrawing group and the leaving group must be ortho or para to each other. The electron withdrawing group and the leaving group have to be ortho or para to each other. And we can see why that is a requirement by taking a look at the mechanism, the SNAR mechanism. And in this case, it starts with nucleophilic attack to the ring instead of the nucleophilic attack of the ring. What will look similar is that we will have a set of resonance stabilized intermediate ions except instead of being cations, they're anions. Where the previous example involved something called for electrophilic aromatic substitution, the intermediate ionic structure was called a sigma complex. This one is called a Mesenheimer complex. But it is a series of resonance stabilized intermediate ions. In this case, it's an anion. And so what I want to do is now I'm going to spread out the nitro group. And what I want to show is how the nitro group can serve as an electron sink that stores electron density. So I'm actually showing the electron withdrawing group withdrawing electron density out of the ring. Now I'm going to show an intermediate. I could show this by skipping that particular resonance structure that I'm drawing now and going right to the end, but I want to be somewhat consistent with what you guys may see in other locations. And so I'll show this final step. Where I push off the benzene ring, or I push off the bromine and accomplish the overall substitution. Okay, there's lots of different ways to show this. There's multiple ways to show this. I could have definitely just said, I could have done it like that. That certainly would have been okay, I think. What I want to show is that the negative charge can be delocalized in the ring at every location, the same way as the positive charge in the sigma complex can be delocalized in every position. I also wanted to make sure that I showed that the electrons can be sort of stored down in the nitro group, in that electron withdrawing group. And that's not clear unless you kind of move the electrons down in that into that position, showing the resonance there. Okay, and so this is the reaction for nucleophilic aromatic substitution. and the mechanisms associated with it. And I gave you the 3 rules. And so this is really the limitation of it. You've got to have an electron withdrawing group. It's going to be like a nitro group. You've got to have the leaving group, like a bromine or a chlorine, be in an ortho or para position to that nitro group. In that case, you can accomplish the transformation, the substitution, by replacing it with an OH, with replacing the bromine or the chlorine with an OH group. So this will come in handy when you want to combine electrophilic aromatic substitution with nucleophilic aromatic substitution in order to solve synthesis problems. So you might run across a synthesis problem where both of those types of reactions are required. All right. So let's go next. So there's one more type of reaction in this chapter. It's called elimination addition. It has in my opinion, it has very limited synthetic practicality. It has very limited synthetic practicality. And here's the example of a type of elimination reaction that would be synthetically useful in any way. You can react it with sodium hydroxide at very high temperatures, followed up by acid workup, and I can get an OH group where the chlorine is. Another example that isn't particularly synthetically useful, but is what establishes the mechanism by which this by which this reaction proceeds, would be an example of something like this, where I have sodium amide in liquid ammonia followed by an acid workup. And this is what we get. This is why it's not synthetically useful. In other words, I don't think we could use it to solve synthesis problems, because we get essentially a 50-50 mixture of the meta product and the para product. The reason why we want to bring this reaction mechanism up is that it can't be explained by the electrophilic aromatic substitution reaction. Well, it's not doing electrophilic aromatic substitution, nor can it be explained by the nucleophilic aromatic substitution. So I can't explain. I could show the mechanism with the amide acting as a powerful nucleophile, but I can't then explain the regiochemical outcome of the 50-50 mixture of meta and ortho products with the same mechanism that I just showed you. You can show the nitro group being an electron sink in the ortho position and the para position, but not in the meta position. So we needed another reaction mechanism to explain this, and that's where the elimination addition mechanism comes in. And so what I'll do is I'll show that mechanism from the perspective that we just saw. So I've got a chlorine reacting with an ortho from the para, para from that methyl group. And so what happens is it starts with proton transfer to form an intermediate anion but it doesn't do anything to the aromaticity in the ring. So there's the formation of this anion, and here's the elimination bit. This is why this mechanism is, I think, of interest. It's because of this particular intermediate structure that's formed. This is a benzene intermediate. Okay. Now, once I have the benzene, I can have the amide come along, and it can attack in two different locations. It can attack there, or it can attack there. And I think you'll see that either of those two locations will lead to the different meta and para substituted product. Now, for simplicity's sake, I'm going to show only the formation of the para product, because I'm going to need to have another arrow to show what happens to the triple bond, because it can't violate the octet rule, even though having a triple bond inside of a 6-membered ring should be somewhat mind-blowing at this point. Then it's some base that comes along, and in this case, I think we could say it's ammonia or acid. Let's call it or it's an acid that comes along is how it's functioning. To form the product. And then the other product we didn't show. The other mechanism we didn't show just depends on which side of that benzene intermediate that next nucleophile adds to. And so this is elimination addition. And again, in the mechanism, we can see here's the elimination piece and here's the addition piece. And it goes through the benzene intermediate. And that's what's cool about that. All right, so what I want to do is I want to just pause there for a nice long beat, nice long minute, and see if there's any questions about any of that stuff. Because that's it. That's all of the chapter that is involved with reactions of benzene rings, aromatic substitution reactions. We talked about electrophilic aromatic substitution, nucleophilic aromatic substitution, and elimination addition. Well, electrophilic aromatic substitution took up most of our time, but these other two reaction types are pretty important as well. So are there any questions about that? Because that's it. Everybody okay? Can I get a one in chat if you're still there? 2, 3, 4, 5, 6. Dylan doesn't want anyone else to know he's there. Send it to me privately. There he goes. Jack's here. All right. Okay. So electrophilic aromatic substitution, or substitutions involving aromatic rings, really was an example of taking one mechanism, especially when it comes to electrophilic aromatic substitution, and just digging really deep into that one mechanism and thinking about it from, I don't want to say thousands, but thinking about it from many different perspectives. What we're doing next, what we're moving on to next, is the chapter about aldehydes and ketones. And the thing about aldehydes and ketones is that it's not one mechanism where we're going to dig in really deeply. There's a lot of mechanisms. There's like 6 or 7 different mechanisms in this one chapter. And the thing that I'd like to warn you guys about, especially if you're looking at this later on in the future, is that they're not necessarily the same, and they have a lot of steps involved with them. If we're thinking about the basic mechanistic moves, proton transfer, nucleophilic attack, loss of a leaving group, or carbocation rearrangement, and we think about just the 4 types of possible moves that a mechanism can have, some of these have combinations of 6 and 7 of these steps in one mechanism. And then there's 6 or 7 or 8 or 9, I don't actually know off the top of my head, maybe it's even 10 different mechanisms in this one section that you have to know. And so there's a lot of chemistry that's involved, especially when it comes from learning different mechanisms as opposed to the same mechanism really in depth. All right, we're not going to get to any mechanisms in this video. We're not going to get to any mechanisms today. What I want to do right now is go over some basics of nomenclature. How do we name aldehydes and ketones? And then I want to review the reactions that we should already know that make aldehydes and ketones. And then we'll leave it there for the day and we'll move on after that. And so let's get going on with the naming business. All right, so aldehydes and ketones involve carbonyl groups. I think at this point in your chemistry life, you should know that that's a carbonyl group. We have 2 different types of molecules that we want to think about: aldehydes and ketones. A lot of the rest of this course will be dedicated to carbonyl chemistry, or chemistry that has to do with carbonyl groups, even if it's at maybe this position. And aldehydes and ketones are the simplest carbonyls. And so we'll talk about carboxylic acids and esters and that kind of stuff later on, but we're going to start off with carbonyls today. And so let's get into it. What is an aldehyde? An aldehyde is where the carbonyl group is at the end of a carbon chain, and a ketone is where the carbonyl group is sandwiched in a carbon chain. So the aldehyde has to have a hydrogen attached to one side, and the ketone has to have carbons attached on both sides. Usually every organic chemistry instructor spends a little time talking about what are the common uses in everyday life and industry when it comes to a particular functional group. I particularly like to talk about aldehydes and ketones because these are the molecules that are usually associated with flavoring and smell. Vanillin, and I'm just going to use the examples that are found in the text, but vanillin, that's vanilla flavor. And here's something you might like. This is, you should know the name of this, benzaldehyde. This is almond flavor. vanilla flavor. Okay, so that's why I like them. Yeah. It's interesting to know the molecules that are responsible for producing the flavors that we like to have in our mouths. If you ever use almond extract, it's got a lot of benzaldehyde. The flavor associated with Fritos, and I'm talking about the corn chip, is not an aldehyde or a ketone. I think it's a cyanide group. I'm starting to get distracted though, thinking about what it is. I don't know off the top of my head. I promise I'll get to it another time. But yeah, the flavor of Fritos is brought to you by some sort of chemical functional group that we're used to, and I think it's a nitrile group. We'll go from there. It is a nitrile, acetonitrile. Everybody loves Fritos, right? No? Nobody likes Fritos? I love Frito pie. I'm from Texas. All right, so I digress. All right, so let's do naming. What? Doritos, Cheetos, then Fritos. Josh is trying to cause trouble. Fritos with pie? What the hell? Frito pie? Is that what that is? You don't know what Frito pie is, Dylan? Oh, no. So you take Fritos in a bowl. Yeah, you put chili all over it, and then you smother that in cheese and onions. That's Frito pie, baby. Yeah, that's good stuff. Right, exactly. Alexa, Fritos are not gross. Yeah, that's my kind of pie, right? Yeah. Yeah, walking tacos. It's like a walking taco. A walking taco is a variation on the Frito pie. Traditional Frito pie would be chili. Yeah. All right. So how do we do this? Aldehydes are named with the suffix aldehyde. So if I did 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 6 carbons in a carbonyl group followed by a hydrogen, this would be hex aldehyde. Not much going on there, hexaldehyde. What if I added something like this to it? Uh-oh. Now all of a sudden is it 1, 2, 3, 4 methyl, or is it 1, 2, 3 methyl? Well, of course, the aldehyde is the priority functional group. So making this a little bit more legible, it would be 3 methyl hexaldehyde. And what am I also subtly reminding you that you need to be able to do? Chirality, exactly. So what's the priorities? 4 is pointing away from you. This is 3. This is 2. This one will be 1. The aldehyde group is going to be closer because of the numbering. Or not. I know in this case because of the numbering, it was the choice between 3 or 4. The aldehyde group is 1, 2 spots away. 2 spots away is a CH2. So that's 1, 2, 3. That's going in the clockwise direction. So that's R, 3-methyl hexaldehyde. Yep. Ketones are named as anones. So if I had 1, 2, 3, 4, 5, 6, and I put the ketone in the middle, I first realized that, oh, I can make it a ketone with 6 carbons, and the ketone can be in a lot of different locations. It can't be in the first position, and I don't need to, on the aldehyde, I don't need a 1 to tell the reader where the aldehyde is, because that's where it has to be. It has to be at the first position, otherwise it's not an aldehyde. It's a ketone in that case. But that does bring me into what I'm just talking about now, which is I do have to tell the reader where the ketone is, because I do have more than one option here. So in this case, the very first one would be 3-hexanone, and this one would be 2-hexanone. And so I can get a little bit more variety with ketones than I can with aldehydes. But at the end of the day, I'm still needing to remember everything that's associated with naming. The simplest aldehyde is formaldehyde. And that one is definitely commonly still used name. Formaldehyde, definitely. So it's good to know that one. Okay. Wrapping up naming, and let's just do a little bit of review of the chemical reactions that we should already know. And then we'll wrap it up for the day. All right, so how can we make some aldehydes? I know that we can oxidize a primary alcohol. What's one of the ways that we can do that? Can I use sodium dichromate to do this? Can I do that? Is that possible? I can oxidize it, but I can't form an aldehyde or a ketone with it. So I need to do, it's too strong. I need something a little weaker. So like PCC with CH2I2, or sorry, CH2Cl2. Or there was some other stuff, or DMP was one of them with CH2, Cl2, and then there was also the DMSO, Swern, right, Swern oxidation, you got it. And that'll form an aldehyde. How else can I form an aldehyde? This one might take you way back to old school. What if I do ozonolysis? Ozonolysis. I'll get 2 aldehydes in this case. Okay. Now I'm going to be able to use this same reaction to get ketones, and I'll show you that again in a second. And then don't forget that if I do the anti-Markovnikov oxidation of an alkyne, it doesn't produce an enol, or it does, but the enol then rapidly tautomerizes to a ketone or an aldehyde. In this case, it would be the aldehyde. So there's some ways to make aldehydes. We should know all of these already. And let's think about some ways to make some ketones. How do we know how to make ketones? Well, we can oxidize an internal alcohol, a secondary alcohol. We can use almost any of the oxidation methods that we talked about before, but in this case, I can also use sodium dichromate. This one is just fine. That'll work as well. Like I said before, we can do oxidation of an alkene, but it has to be It has to be more than disubstituted. It has to be disubstituted on the right side as well. But this oxidation, O3 and DMS, will also get a ketone. Just like there was anti-Markovnikov oxidation of alkynes, there's also Markovnikov oxidation of alkynes with good old H2SO4 and water. It works just the same way with alkenes, except the only difference is this mercury sulfate as part of the reagent. Again, it doesn't form an enol. It forms a ketone because of the tautomerization. And then one last little bit. Just a reminder, we just learned how to use an acid chloride to do Friedel-Crafts acylation. So that's also a way to make a ketone. And those are all the ways that we know, or a good summary of the different ways that we know on how to make aldehydes and ketones. And so as promised, what I'm going to do is I'm going to leave it there, and we'll start to go into mechanisms and reactions pretty quick. It starts off pretty slow, but there are some mechanisms that really get into it. And so let me actually give you a count. I want to make sure that I got a count. Let's see. I want to give you an idea of how many mechanisms there are in this chapter. I'm looking at least 14 mechanisms. That's it. We'll do those. We'll start off with those 14 mechanisms and all the reactions associated with them next time.